Usually, when we talk about a hard drive or like a massive physical storage array in an enterprise data center, there's this inescapable expectation of physical limitations.
Right.
It's like managing a physical warehouse, you know? You rent the building, you build the steel shelves, you start filling them with boxes, and, well, eventually the shelves just get full.
Yep.
And the warehouse manager just points to the ceiling and says, "That's it. We're out of square footage. Go buy another building."
It's a completely finite binary reality. I mean, the disk is either full or it's not. The physical platter can only hold so many magnetic bits, right?
Right.
And when you hit that wall, your application stops writing data. It just crashes.
But then you step into the world of modern cloud infrastructure, and suddenly that warehouse has no physical wall.
Yeah, the ceiling just evaporates.
Exactly. We're looking at a storage landscape today that is, for all practical intents and purposes, infinite. And because it's infinite, the underlying engineering is highly, highly complex. Oh, absolutely. It forces us to completely rethink the physics of how we save and retrieve information. Because when you remove the boundary of a physical hard drive, you stop managing disks and you start managing distributed data physics at a planetary scale.
At a planetary scale, which is why today we are pointing our microscope at the foundational technology that essentially powers the modern web. We have a massive stack of technical documentation, architectural blueprints, engineering case studies, and pricing manuals.
Oh, the pricing manuals are a whole journey on their own.
They really are. And performance optimization guides all centered around Amazon S3.
Right, simple storage service. Though, let's be real. To the engineers managing petabytes of data today, the word simple is doing an incredible amount of heavy lifting this far into its lifespan.
It really is doing the heavy lifting. I mean, most people conceptualize S3 as just a place to dump files, right? Like a giant digital attic where you put your backups and your JPEGs and just, forget about them.
Yeah, that's the standard view.
But if we dig into the original internal design philosophy from the Amazon engineers back in 2006, they didn't set out to build an attic. They built what they called the mallet for the internet.
I love that phrase. Mallet for the internet is just the perfect conceptual anchor for everything we're going to discuss today.
Yeah, let's unpack that, because for those listening who might not spend their days writing C or C++ code, mallet stands for memory allocation.
Right.
When a programmer writes a basic application, they rely on that mallet command to effortlessly carve out RAM for their program to use. They just say, I need this much memory, and the operating system hands it to them.
Exactly. The programmer doesn't need to know which specific, Kingston RAM stick the data is sitting on.
Right. They don't care about the motherboard bus speeds or which sector of the silicon is being activated. They just ask for space, and it's there.
And that exact abstraction is what S3 brought to the internet. It was built to be a bottomless, API-driven memory bank for the entire web.
Which is wild to think about.
Yeah. You don't rack servers. You don't provision SAN arrays. You don't format file systems. You simply send an API request that says, put this data here, and the infrastructure absorbs it.
And that abstraction is why S3 has scaled to a degree that is almost difficult to comprehend.
Yeah.
I mean, we are talking about a system that now holds hundreds of trillions of objects, not billions. Trillions.
Yeah, it's a staggering number.
It routinely handles hundreds of millions of requests every single second of the day. It's not just a product AWS sells, it's the foundational dependency for AWS itself.
Oh, exactly. Massive compute services like EC2, data warehouses like Redshift, query engines like Athena, they all use S3 as their underlying object store.
So if you treat S3 like a basic file system, like the C drive on your laptop, what happens?
Well, you will inevitably hit performance bottlenecks. You'll run into cost overruns that can cripple a startup or completely bankrupt an enterprise project.
Because it's not a C drive.
No, not at all. S3 is a highly evolved, globally distributed data engine, and you have to understand the mechanics of that engine to drive it properly.
Okay, so let's open the hood on that engine. I want to start with the most fundamental question. How does S3 actually scale to handle millions of requests a second without just melting down?
That's the big question.
Because if I have a folder full of photos on my laptop and a million people try to open one of those photos at the exact same millisecond, my hard drive spins out of control. The CPU pegs at 100%, and my laptop basically turns into a puddle of molten plastic. How does S3 avoid the puddle?
Right. Okay, so to understand that, the very first thing you have to unlearn is the concept of a folder.
Okay.
S3 does not use traditional hierarchical file systems. It uses a completely flat namespace.
But wait, When I look at S3 in the AWS console, or if I use the command line, it looks exactly like folders. Like I see a path like bucket data 2026 image.jpg. That looks identical to the directory tree on my map.
Oh yeah, it totally does. But it's an illusion designed for human comfort. Under the hood, that isn't a nested directory structure. There is no data folder that contains a 2026 folder. The entire string data 2026 image.jpg is simply one single unique identifier for that object. It's the key.
So the slashes aren't structural boundaries at all.
Exactly.
They're literally just characters in the text string, no different than an A or a B.
Precisely. But here's the critical mechanism. S3 scales horizontally by creating internal index partitions based on what we call prefixes.
Prefixes.
A prefix is any leading substring of that object's key. S3 monitors the access patterns of your keys, and it uses those prefixes to internally shard or slice up the index of your data across its massive fleet of internal servers.
Okay, sharding the index. Let's make this tangible for the listener. If S3 didn't shard the index, what would happen?
Well, if S3 kept one giant master list of every file in your bucket on a single internal server, that single server would become the bottleneck immediately. 1 million requests hit that server, its CPU maxes out, and the system fails. Sharding means S3 takes that master list and chops it up. It puts a list of all files starting with A on server 1, files starting with B on server 2, and so on. Now, the read and write load is distributed across the entire fleet.
And the rules governing how and when S3 does this sharding change dramatically, right? Because the sources highlight July 2018 as this massive fundamental watershed moment for S3 performance. What was the reality for engineers before that date?
Oh, it was a much more constrained environment before 2018. Back then, S3 throttled buckets at a global level, and the limits were incredibly low by today's standards.
How low?
A single bucket could only sustain roughly 100 write requests per second, and that includes POT, copy, and delete commands, and about 300 get requests per second. If you pushed past that, the internal partitioning system would struggle to keep up, and you'd just get throttled.
Wow. 100 writes a second. I mean, you're building a social media app or processing IoT telemetry data from thousands of sensors. 100 writes a second is nothing. You'd hit that ceiling instantly.
Absolutely instantly.
So how did developers build high-scale apps on S3 before 2018?
They used a very specific workaround. AWS explicitly instructed developers to introduce entropy, basically randomness, at the very start of the object T.
Okay.
The best practice was to take the file name, generate an MD5 hash of it, and prepend those random hexadecimal characters to the front of the prefix.
So if my application naturally wanted to name a file based on the date, like 218501 sensordata.json, I wouldn't do that.
No, you wouldn't.
I would hash it, and the file name would become something totally unreadable, like 8B3208218005 sensordata.json.
Yes. And by forcing those random characters to the front of the key, developers artificially forced S3 to spread the data across dozens or hundreds of different internal partitions.
Ah, I see.
It ensured that no single physical index server was taking all the writes for that particular day. It bypassed the 100 requests per second bottleneck entirely.
But here's where it gets really interesting, because the documentation and architecture guides today are flashing giant red warning lights about this exact practice.
Oh, big time.
They explicitly state that if you randomize your prefixes today, you are actively hurting your performance. Old habits die hard, I know. But why is this brilliant workaround from 2017 now considered a toxic anti-pattern?
Because in July 2018, S3 completely rewrote its scaling engine. It abandoned the global bucket limits and shifted to a model where it automatically scales per partitioned prefix.
Per prefix.
Yes. Today, a single partitioned prefix can natively handle 3,500 write requests and 5,500 read requests per second.
Let me stop you there because I want to make sure the math is clear for everyone listening. You're saying those thousands of requests aren't for the whole bucket, it's per prefix.
Per prefix, exactly. There is no functional limit to the number of prefixes you can create in a bucket.
Wow.
So if you have 10 distinct active prefixes in your bucket, the S3 infrastructure scales out to give you 55,000 reads per second. If you have 100 prefixes, you instantly have 500,000 reads per second capacity. The system scales horizontally based on the structural logic of your naming convention.
Okay, so the ceiling was essentially lifted. But that just means hashing isn't necessary anymore. Why does hashing actively hurt us now?
Because randomly hashing the start of every file name destroys a critical property called lexicographic locality.
Lexicographic locality.
Right. Think about how modern analytics engines work tools like Amazon Athena, AWS Glue, or Apache Spark. They rely on logical, structured, date-based, or category-based partitions to query data efficiently.
Right, like if I ask Athena to show me all the sensor errors from May 1st, 2026, and my keys naturally start with 2026-0501, Athena looks at the S3 metadata and knows exactly where that data lives. It just ignores the rest of the bucket.
Exactly. But if you have hashed the prefix, that date string 2026-0501 is buried behind random hexadecimal garbage. Athena can't use the prefix to filter the data.
Oh, no.
Yeah, it has to scan every single partition and open every single file in the bucket to see if the date matches inside. A query that should have scanned 10 megabytes of data and cost a fraction of a cent suddenly turns into a massive, full table scan that processes petabytes of data and costs thousands of dollars.
That is brutal.
You are optimizing for a bottleneck that AWS engineered away 6 years ago, and in doing so, you are breaking the core mechanics of your analytics engines.
It's like building a complicated maze in your front yard to confuse a burglar who retired a decade ago, and now the mail carrier can't deliver your packages. You're just punishing your own systems.
That is a brilliant way to put it.
But let's talk about the physical mechanics of this automatic scaling. You said S3 auto partitions when a prefix gets hot. But software takes time to allocate resources. It's not instantaneous. What happens in the milliseconds between when traffic spikes and when S3 finishes scaling?
That gap is where you encounter the infamous HTTP 503 slowdown error.
Ah, the 503.
Yeah, the auto-scaling is seamless from an administrative perspective, but physically, S3 has to recognize that a specific index partition is getting too hot, allocate new hardware resources behind the scenes, and physically split the index data into two new partitions. During that brief window, S3 will return 503 errors to the client application, telling it to back off.
I was visualize this like a massive public library.
Okay, let's hear it.
Imagine 100 patrons run through the doors at the exact same moment, and they all sprint to the exact same shelf to grab the exact same popular book. There's a massive physical traffic jam in the aisle.
Right.
The librarian sees the mob, realizes the shelf is overwhelmed, and frantically starts building a second identical shelf across the room to split the crowd. While the librarian is hammering the new shelf together, they are yelling at the crowd, "Slow down, give me a minute." That's the 503 error.
That's actually a very accurate mental model, and a well-architected application knows how to deal with an overwhelmed librarian.
How so?
Well, the AWS SDKs that developers use have built-in mechanisms for exponential backoff and jitter. When the SDK receives a 503, it doesn't just hammer the API again immediately. It waits 100 milliseconds, tries again. If it fails, it waits 400 milliseconds, then a second, then 2 seconds.
Giving the librarian time.
Exactly. By the time it retries the fourth or fifth time, the librarian has finished building the second shelf, the internal partition is split, and the traffic flows smoothly.
But developers can still inadvertently sabotage this auto-partitioning process, right? Even without using the old hashing trick, the documentation specifically warns against something called the sequential anti-pattern. What is that, and why does it break the librarian's ability to split the shelf?
So the sequential anti-pattern happens when you use a naming convention that increments very slowly at the beginning of the string. The most common examples are database backups or transaction logs that use sequential IDs. Bucket data 000000001, bucket data 000000003,
Or using raw Unix timestamps in milliseconds where the leading digits don't change for days at a time.
Yes.
But from a human perspective, that makes perfect logical sense. File 1, File 2, File 3.
It makes sense to us, sure, but it's catastrophic for S3's partitioning engine. Remember, S3 looks for prefixes, the leading characters, to decide where to split the index.
Oh, right.
If thousands of files arrive and their keys all begin with the exact same characters, bucket data 00000S3 cannot find a logical string variance to cleanly slice the partition in half.
Because it's all zeros.
The prefix is entirely homogeneous. So going back to your analogy, the librarian sees the mob, but all the books have the exact same title, so they don't know how to divide them logically between the two shelves. The single internal partition just keeps getting hotter, and you drown in 503 errors because the auto-split mechanism is paralyzed.
So how do you fix it? Because we just established that we can't go back to the random hashing trick because that breaks our analytics. We need structure, but we need high performance.
You solve it by introducing a high cardinality dimension early in the key, but in a deterministic, structured way.
Like what?
For example, if you are a SaaS platform storing logs for thousands of different customers, don't put the date first. Put the tenant ID or the customer UAUB first. So the pass becomes tenant A 2260501 log and tenant B 2260501 log.
Ah, So because tenant A and tenant B are wildly different strings right from the very first character, S3 sees that variance and can easily put tenant A on one internal partition and then tenant B on another.
Exactly. You get horizontal scale naturally. If you absolutely must use purely sequential numbers and you have no other identifiers to use, there is a very clever architectural trick. Reverse the digits of the sequence number.
Reverse them. You mean literally flip the string backwards. So 0000001 becomes 100,000.
Yes, exactly. Think about how a sequence number grows. The ones place changes constantly. 1, 2, 3, 4, 5. The millions place might not change for months.
Right.
By reversing the string, you take the most rapidly changing digit and place it at the very front of the prefix. S3 sees 100, 0, 0, 200, 300, 0. It instantly sees a massive spread of distinct leading characters.
Wow.
Yeah, so the partitioning engine can cleanly slice the data across its infrastructure, avoiding the bottleneck, while your application still maintains a deterministic, reversible naming convention.
That is such an elegant workaround. You just flip the string, and suddenly the entire cloud infrastructure can handle your traffic spike.
It's all about playing into the physics of the system.
But so far, we've only been talking about optimizing request rates, right? Handling thousands of tiny log files or database writes per second. What happens when the problem isn't the number of files, but the raw, massive size of the files?
That's a whole different ballgame.
We've figured out how to stop the library from catching fire when 1 million people ask for a text file. But what happens when, instead of a text file, a media company in Tokyo wants to upload a 500 gigabyte uncompressed 4K video file to a bucket in Virginia? Clever prefix tricks don't solve the fact that pushing half a terabyte through undersea fiber optic cables is subject to the physical limitations of the internet.
And that transition from logical scale to physical scale is where a lot of architects struggle. When you upload a massive file natively over the public internet, you are fighting against the Standard Transmission Control Protocol, or TCP.
Right.
TCP is the backbone of internet communication, but it is incredibly sensitive to latency and packet loss.
Because the data doesn't just fly in a straight line from Tokyo to Virginia.
Exactly. Your data packets are bouncing across dozens of different internet service provider routers, exchange points, and undersea cables. Every single hop introduces a tiny bit of latency, and if a single router is congested and drops a packet, TCP's congestion control algorithms kick in.
And it throttles you.
Yep. The protocol assumes the network is overwhelmed, so it drastically shrinks the TCP window size, essentially reducing the amount of data it's willing to send at once. It deliberately slows down the entire transfer to ensure data integrity. Over long geographical distances, this creates a massive bottleneck.
So how does AWS bypass the public internet? Because they can't change the speed of light, and they obviously can't rewrite TCP for the whole world.
They bypass it by leveraging their own private infrastructure through a feature called S3 Transfer Acceleration, or S3TA.
Okay, how does S3TA work?
When you enable S3TA on a bucket, your upload doesn't attempt to travel over the unpredictable public internet all the way to the Virginia data center. Instead, AWS routes your upload to the absolute closest Amazon CloudFront Edge location.
CloudFront is their content delivery network. So if my user is uploading from an office in Tokyo, the file just goes to the AWS Edge location down the street in Tokyo.
That's right. The data only travels a few miles over the public internet. Once it hits that Tokyo Edge location, the data is immediately routed onto AWS's private, dedicated global backbone network. This is a highly optimized, custom-engineered fiber optic network that AWS controls end-to-end. There is no public congestion. The routing paths are optimized.
It's the difference between trying to drive a semi-truck full of data across the country on public highways, dealing with stoplights, potholes, traffic jams, and detours, versus driving that truck a few blocks to a private, high-speed bullet train terminal where the data gets loaded onto a private track that goes straight to the destination with 0 stops.
The bullet train analogy is perfect, honestly, because the benchmarks in the documentation prove the physical impact of that dedicated path. They tested uploading a 485 megabyte file across a massive geographic distance. Doing it natively over the public internet took roughly 72 seconds. Simply flipping the switch to use S3 transfer acceleration dropped that exact same upload down to 43 seconds.
That's a huge improvement. But the sources indicate we can push it even further.
Yeah.
We can combine S3TA with something called multi-part uploads. What is the mechanism behind a multi-part upload?
So for large files, AWS strongly recommends and actually mandates for files over 5 gigabytes that you do not send the data as one massive continuous stream. A multi-part upload takes that 485 megabyte file and slices it into smaller chunks on the client side, say 10 megabytes each.
Okay.
Then the application uploads all of those 10 megabyte chunks to S3 in parallel, establishing multiple simultaneous TCP connections.
So if we go back to the truck analogy, instead of one massive heavy semi-truck slowly driving 485 megabytes down the highway, you slice the cargo up and put it into 50 smaller, faster trucks, all driving side by side on a 50-lane highway at the exact same time.
Precisely. By uploading in parallel, you bypass the limitations of a single TCP stream. You fully saturate the available bandwidth of the user's internet connection. And crucially, it adds a massive layer of fault tolerance.
Fault tolerance.
Yeah, think about the physical reality of a single stream upload. If you are transferring 500 gigabytes and the internet connection blips at 99%, the TCP connection drops. You have to start the entire 500 gigabyte upload over from zero.
Oh man, that is soul-crushing.
It's expensive and slow. But with a multi-part upload, if the network blips and one 10 megabyte part fails to transfer, the SDK simply retries that one specific 10 megabyte part. The other 49 parts are unaffected. S3 receives all the parts and then transparently reassembles them back into the single large object inside the bucket.
That is brilliant. So when we combine this parallel fleet of trucks with the private bullet train tracker transfer acceleration, what happens to our benchmark?
The compounding effect is massive. That 485 megabyte upload, which originally took 72 seconds natively, drops down to just 28 seconds. You are cutting the total transfer time by more than 60% just by understanding the physics of the network.
Okay, I have to play devil's advocate here. As an architect, this sounds incredible. Blazing speed, private backbones, parallel TCP saturation, fault tolerance. But I know how cloud providers operate. This cannot possibly be free. S3TA uses expensive global edge locations and private fiber. What's the catch?
You're entirely right to ask, because data physics translates directly into data economics. S3 transfer acceleration adds a strict surcharge of $0.04 per gigabyte transferred. That applies to data moving into the bucket and data moving out.
4 cents a gigabyte. Now, to a casual listener, 4 cents sounds trivial. But if I'm running a global media application, or I'm ingesting petabytes of autonomous vehicle telemetry data every month, 4 cents a gigabyte multiplied by a petabyte is going to become an astronomical line item on the monthly AWS bill.
Oh, it scales linearly, and it becomes very expensive very fast. However, AWS engineered a very clever performance-based pricing model for S3TA. They don't just charge you blindly.
They don't.
No. The infrastructure constantly monitors the network routing performance in real time. If you initiate a transfer using the S3TA endpoint, and AWS's internal telemetry determines that routing the data through the edge location is not actually faster than a direct public internet upload, maybe the user happens to live 5 miles away from the primary S3 data center anyway. AWS will seamlessly route the traffic directly, and crucially, they will not charge you the $0.04 surcharge for that specific transfer.
Wait, really? So you only pay the acceleration toll if it actually accelerates the data?
Exactly. You only pay for a measurable speed improvement. If the fast lane is congested, they route you on the regular highway and refund your toll.
That is a remarkably fair pricing model. And speaking of money, I think this is the perfect moment to transition into the economics of S3. Because we've figured out how to saturate a fiber line to get data into Virginia at blistering speeds. But now the data is just sitting there. And if we leave a petabyte of data sitting there indefinitely, the CFO is going to have a heart attack when the invoice arrives.
So true.
Moving data fast is an engineering challenge. Storing data forever is an economic challenge.
It is the eternal conflict between cloud engineering and enterprise accounting. And the friction usually stems from a fundamental misunderstanding of what you're actually buying. People inherently assume S3 pricing is analogous to buying a hard drive at Best Buy. They think the only metric that matters is how many gigabytes are on the disk.
But S3 isn't a hard drive. It's a managed service. And the documentation outlines a highly complex, multi-dimensional matrix of costs. We aren't just paying for gigabytes. What are the actual dimensions of an S3 bill?
So there are 6 distinct pricing dimensions. First, yes, you pay for the pure storage volume, the gigabytes at rest. But second, you pay for requests and retrievals. Every single time your application makes an API call, every put UT, get T, list, or copy Y, you are charged a tiny fraction of a cent.
Okay, that adds up.
Third, you pay for data transfer, specifically egress bandwidth, which is moving data out of S3 to the public internet. Fourth, you pay for management and analytics tools, things like S3 inventory reports or storage lens. Fifth, you pay for replication bandwidth if you are continuously copying data to a backup bucket in another geographic region. And sixth, you pay for transform functions, like using S3 object lambda to process data on the fly.
So every single interaction with the bucket, whether it's reading a byte, moving a byte, or just asking for a list of files, is a meter ticking in the background.
Exactly.
But the biggest, most impactful lever an architect has to control the baseline storage cost is choosing the right storage class. Before we break down the 8 different storage classes, I want to highlight the statistic from the sources that is genuinely mind-boggling. Across all the primary S3 storage classes, AWS guarantees what they call 11 nines of durability.
99.999999999% durability.
I want to translate that percentage into physical reality for the listener. If you store 10 million distinct objects in S3, statistically speaking, you might lose exactly one of those files every 10,000 years.
The engineering behind that is staggering. To achieve 11 nines, AWS doesn't just save a file to a disk. They use complex mathematical algorithms called erasure coding.
How does that work?
When you upload a file, S3 breaks it apart into smaller cryptographic fragments and distributes those fragments across multiple hard drives in multiple server racks, across at least 3 entirely distinct physical data centers, what AWS calls availability zones, separated by miles of geographic distance. Even if an entire data center loses power, burns down, or gets hit by a meteorite, the S3 infrastructure can mathematically reconstruct your complete file using the surviving fragments from the other 2 data centers.
So the durability is practically absolute. The data is never going to disappear. But if the physical safety of the data is identical across all these different classes, what is the economic lever? Why are the prices so wildly different? What are we actually paying for?
You are paying for 2 things: availability and retrieval speed. Durability means the file won't be corrupted by a hardware failure. Availability means the file is physically accessible to you the exact millisecond your application asks for it. The deeper into the storage tiers you plunge, the cheaper the monthly gigabyte rate becomes. But in exchange for that cheap rent, AWS places physical and economic barriers in front of the data. You have to wait longer to access it, and you pay steeper financial penalties when you do ask for it.
Okay, let's walk through this matrix. Tier 1, S3 standard. I'll take this one because it's the baseline. This is the default. It offers high throughput, single-digit millisecond latency, and multi-AZ redundancy. There are no minimum storage duration limits. You can store a file for an hour and delete it. And crucially, there are no data retrieval fees. You just pay the flat storage cost, which hovers around 0.023 orders per gigabyte per month. This is for hot, active data that your users are querying constantly.
Right.
But then we look at Tier 2, S3 standard infrequent access, or standard IA. The physical characteristics are the same: millisecond latency, multi-AZ redundancy, but the price drops by almost half to roughly below 0.0125 per gigabyte. Now, if I'm a junior architect looking at this pricing page, it feels like a trap. Why wouldn't I just put every single file in a standard IA from day one and instantly cut my AWS bill in half?
Because AWS implements 3 specific financial mechanisms to penalize you if you use IA for hot data. First, there is a per gigabyte data retrieval fee. Unlike standard, where reading data is free, every time you download or read a file from IA, you pay a penalty. If you have a popular image that gets read thousands of times a day, the retrieval fees will massively eclipse the storage savings.
So it's literally designed for infrequent access. What are the other 2 catches?
The second is a 30-day minimum storage duration penalty. If you put a temporary log file in standard IA and a lifecycle rule deletes it 2 days later, AWS will still bill you for the full 30 days of storage. You cannot churn data in IA.
Okay, makes sense. And the third?
The third, which catches many engineers off guard, is a 128 kilobyte minimum billable object size.
Explain the physics of that. Why does the size matter?
Well, it takes compute overhead and metadata management for AWS to track and store millions of files, regardless of how big they are. If you store a tiny 5 kilobyte text file in standard IA, AWS will artificially inflate the bill and charge you as if that file were physically taking up 128 kilobytes of space.
Oh, wow.
It is a massive mathematical price penalty for small files. If you dump millions of 5 kDB JSON payloads into standard IA to save money, your bill will actually skyrocket because you'll be paying for phantom capacity you aren't using. Standard IA is strictly designed for larger files like complete database backups or large media assets that you don't look at often, but when the CEO asks for them, you need them in milliseconds.
That makes perfect sense. Okay, Tier 3, S3 one-zone IA. This drops the price another 20% down to exactly 1 penny per gigabyte, and the catch here is right in the name, one zone.
Yes, we talked about how S3 achieves 11 nines of durability by spreading data across 3 distinct availability zones. S3 one zone IA explicitly abandons that redundancy. It stores your data on hardware within a single specific availability zone.
So if a massive hurricane floods that specific data center facility, or a backhoe cuts the wrong fiber optic trunk line and isolates that building, what happens?
The data is gone. The 11 nines of durability still apply to the physical hard drives within that specific building. They still use erasure coding across racks. But if the building itself is destroyed or permanently taken offline, your data goes with it. The architectural rule here is absolute. You must only use one zone IA for secondary backups or easily recreatable data, like image thumbnails where the original high-res image is stored safely and standard. You never, ever use one zone IA as the primary source of truth.
A very stark warning. Then Tier 4 is where things get clever, S3 intelligent tiering. The sources refer to this as the autopilot solution. If predicting whether data is hot or infrequent is so difficult and prone to expensive mistakes, this tier just takes the human out of the loop.
It's a brilliant engineering solution to a very common enterprise problem: unpredictable access patterns. Imagine a massive data lake used by hundreds of data scientists. You have no idea which datasets they're going to query this month. If you guess wrong and put hot data in IA, you get crushed by retrieval fees.
Right.
With intelligent tiering, you pay a tiny flat monitoring fee, about 0.0025 per 1,000 objects. In exchange, AWS's internal systems constantly monitor the access patterns of your individual files. If a file hasn't been touched in 30 consecutive days, S3 automatically moves it down to a cheaper, infrequent access tier. If it sits untouched for 90 days, it automatically shifts it down into a deep archive tier.
But what happens when the data scientist suddenly needs that 90-day-old file for a new machine learning model?
The exact millisecond they run a JT request, S3 instantly promotes the file back to the hot, frequent access tier. And here's the magic. There are 0 retrieval fees when the data moves back and forth. The system just continuously optimizes the storage bill while the architect sleeps. For complex workloads with unknown access patterns, intelligent tiering is almost always the most cost-effective default choice.
I love solutions that remove cognitive load. But now we have to talk about the deep freeze. Tiers 5, 6, and 7, the Glacier family. This is where data goes to sleep.
These are the archival tiers, and they reflect a totally different physical reality than S3 standard. First, we have Glacier Instant Retrieval. This is for data you might access maybe once a quarter, but when the audit happens, you still need millisecond latency. Think medical imaging records or old news broadcast footage. It's incredibly cheap to store, about 0.004 per gigabyte, but the per gigabyte retrieval fees are extremely steep to discourage frequent use.
And then we step down into the true archives, Glacier Flexible Retrieval.
This is where we cross a threshold. In flexible retrieval, we lose the millisecond illusion. Retrieving data from this class is an asynchronous process. You have to send an API request asking AWS to restore the data. If you pay a premium for expedited access, it takes 1 to 5 minutes to get your file. If you use standard access, it takes 3 to 5 hours, but it offers a bulk retrieval option that takes 5 to 12 hours, and bulk retrievals are completely free of data retrieval charges. It's the perfect tier for disaster recovery drills or massive end-of-year compliance audits where you know you'll need the data tomorrow.
And finally, the Mariana Trench of cloud storage, Glacier Deep Archive.
The absolute cheapest storage tier AWS offers, we are talking 0.000099 per gigabyte. It is up to 95% cheaper than S3 standard. It is strictly meant for data you are legally mandated to keep for 7 to 10 years for regulatory compliance, but that you realistically hope to never ever look at again.
Because retrieving it is an ordeal.
Yes, exactly. Restoring data from Deep Archive takes a minimum of 12 hours and can take up to 48 hours for massive bulk requests. Physically, you have to imagine this data isn't sitting on spinning high-performance NVMe drives. It's highly compressed, highly erasure-coded, and pushed down into ultra-dense, spun-down storage media that requires physical time and compute power to rehydrate and stage back into a readable format.
So we have this incredible, flexible spectrum of economic choices, from blazing fast NVMe drives to sleeping tape archives. But every complex economic system has hidden traps. Where are the gotchas in this pricing model that end up costing companies thousands of dollars by accident?
Oh, there are 2 major architectural traps that catch teams off guard. The first is what we can call the metadata overhead trap in Glacier. When you transition objects from S3 standard down into Glacier Flexible Retrieval or Deep Archive, AWS appends a 40 kilobyte metadata charge per object
Wait, 40 kilobytes of metadata. For what?
to maintain the global index. Even if your actual file is frozen in Deep Archive and will take 48 hours to restore, S3 still needs to be able to instantly list the contents of your bucket if you run an else or list API call. They can't wait 48 hours to tell you what the file name is, so they must keep 40 kilobyte of index data, permissions, and metadata in warm, active storage.
Okay, 40 kilobytes doesn't sound like much. If I archive a massive 100 gigabyte SQL database dump file, adding 40 kilobyte of metadata to the bill is mathematically invisible.
Exactly. But imagine a different scenario. Imagine you have a massive application generating millions of tiny 1 kilobyte JSON log files every day. If you write a lifecycle rule that pushes 1 billion tiny 1 KB files directly into Glacier to save money, AWS adds 40 kilobyte of warm storage overhead to every single one of those files, you suddenly multiply your total storage footprint by 40. You will be paying exponentially more money for the metadata tracking the files than for the actual log files themselves.
Ouch. So the architectural lesson there is absolute. If you are archiving small files, you must run a compute job to bundle them into a massive tarball or a zip file before you send them to Glacier. One giant file means one 40 KB metadata charge.
Bingo.
What is the second major trap?
The egress trap. This is the silent killer of cloud budgets. Ingress writing data into S3 from the internet is always completely free. AWS wants your data. But egress transferring data out of S3 back to the public internet is expensive. After your first 100 gigabytes per month, AWS charges 0.9 cents per gigabyte for standard data transfer out to the internet.
9 cents. Let's contextualize that against the storage costs. S3 standard storage is roughly 2 cents a gigabyte. Standard IA is 1 cent. But transferring that data out is 9 cents. The bandwidth is 4 to 9 times more expensive than the actual hard drive space.
It is wildly asymmetrical. If you build a popular public website, say a stock photography platform, and you serve large, high-res images directly from an S3 bucket to millions of users around the world, your egress bill will eclipse your storage bill by orders of magnitude within days.
So how do you mitigate that? You can't just tell users to stop downloading photos.
You introduce an architectural buffer. You place a caching layer, specifically Amazon CloudFront, in front of your S3 bucket. CloudFront caches the images at those global edge locations we discussed earlier. When a user requests the photo, they pull it from the CloudFront cache, not directly from S3. Data transfer out from S3 to CloudFront is free. And while CloudFront still charges for egress to the user, the rates are generally lower, and the massive reduction in direct S3 DET requests heavily suppresses the overall bill.
It's all about understanding the flow of the data, not just where it rests. Which actually brings us to a critical pivot point in our journey today. We just spent a lot of time talking about data sleeping in Glacier for a decade to save pennies. But the modern technological landscape isn't just archiving tax returns and medical records.
No, definitely not.
Modern applications, and by that I mean generative AI model training, massive machine learning clusters, high-frequency financial trading algorithms, real-time ad bidding engines. They don't care about cheap archival storage. They need data to move faster than even S3 standard can fundamentally handle.
And that brings us to the physical limitations of S3 standard. Standard gives you a time-to-first byte latency in the low tens of milliseconds. For human perception, 20 milliseconds is instantaneous. But for a distributed machine learning cluster with thousands of NVIDIA GPUs waiting for the next batch of training data, 20 milliseconds is an eternity.
Right. If those GPUs are sitting idle for 20 milliseconds on every single request, just waiting for the network to deliver the data, you are burning thousands of dollars an hour in wasted compute capacity. The storage is bottlenecking the supercomputer.
Exactly. And that bottleneck is what forced AWS to engineer the 8th and newest storage class, S3 Express 1 Zone. This is a tier engineered specifically for consistent single-digit millisecond latency. It is mathematically up to 10 times faster than S3 standard, and it simultaneously cuts API request costs by 50%. But here is where it gets absolutely fascinating for distributed systems nerds. To achieve this kind of blistering speed, AWS had to break their own fundamental religious tenets of how S3 operates, didn't they?
They did, yeah. We spent the last 20 minutes treating the 11 nines of durability across 3 availability zones as gospel. S3 Express 1 Zone completely abandons that multi-AZ redundancy requirement. Just like the IA tier we discussed, it is a single AZ storage class.
So again, if that specific physical data center in Northern Virginia loses power, the AI training cluster goes down, and potentially the working data is lost.
Yes, but unlike 1 Zone IA, which is built to be a cheap attic for backups, Express 1 Zone is built to be an ultra-high-performance engine block for compute. To strip out every possible millisecond of latency, AWS had to introduce an entirely new architectural concept, the directory bucket.
Okay, we established earlier that S3 doesn't use real folders. It uses a flat namespace and scales based on prefixes. How is a directory bucket fundamentally different from the general-purpose buckets we've been using since 2006? It changes the physical reality of the infrastructure in three critical ways. First, a directory bucket scales instantly. Remember the librarian scrambling to build the second shelf? The 503 slowdown errors when a general-purpose bucket tries to auto-partition? Directory buckets do not have a warm-up period. Because of how they pre-allocate index infrastructure, they can handle up to 2 million requests per second the exact second you create them.
2 million requests a second instantly. That is a staggering amount of throughput. What's the second change?
Co-location.
No.
Because directory buckets are explicitly pinned to a single specific availability zone, say US East 1A, it allows architects to perform a physical maneuver. If your compute resources, your massive EC2 instances, your elastic Kubernetes clusters, your SageMaker AI training nodes are physically running in AZ East 1A, you intentionally create your directory bucket in US East 1A as well.
Ah, you are physically putting the hard drive in the exact same warehouse as the processor.
Exactly. The speed of light through fiber optic cable is a hard physical limit. If your compute is in Zone A and your standard S3 bucket is replicating data across zones A, B, and C miles away, the data has to travel. By strictly co-locating the compute and the storage in the exact same facility, you strip out miles of fiber optic cabling and multiple network routing hops. The time to first byte drops vertically.
And what's the third change? Because taking out the physical distance makes sense, but the sources also mention a change to the cryptography and authentication overhead.
Right. General-purpose S3 buckets authenticate every single individual API request. When you send a GET request, the AWS SDK mathematically signs the request using signature version 4. AWS receives it, decrypts the signature, checks your IAM permissions, and then fetches the data. Doing that cryptographic math millions of times a second takes CPU cycles and introduces latency.
You're checking the ID badge at every single door in the building.
Precisely. Directory buckets change this by using a session-based access model. Your application calls a new API, S3 creates session. It authenticates heavily once, and S3 hands back a temporary, highly optimized session token. For the next 5 minutes, your application just passes that token with its reads and writes. S3 bypasses the heavy SIGV4 cryptographic validation on every single object. It shaves off tiny fractions of a millisecond on every call, which, when multiplied by 2 million requests a second, results in massive compute and time savings.
It is a masterclass in relentlessly stripping away every possible millimeter of friction. You take away the cross-region replication, you take away the fiber optic distance, you take away the cryptographic per request overhead, and you're left with pure, unadulterated speed. But co-locating blazing fast storage next to compute is only half the battle for modern analytics. Because as the sources point out, raw objects, just dumping billions of CSVs or JSON files into a bucket, are not an efficient format for these AI and machine learning workloads. S3 is evolving. It's no longer just a dumb object store where you put a file and get a file. It is transforming into a managed, structured data engine, which leads us to S3 tables.
S3 tables represents a massive paradigm shift. Traditionally, if a massive enterprise wanted to run SQL queries across petabytes of data sitting in S3 using a query engine like Amazon Athena or Apache Spark, they couldn't just query raw CSV files efficiently. They had to introduce open-source table formats, primarily Apache Iceberg.
Let's unpack that for a second. Why Iceberg? Why can't a supercomputer just read a CSV file?
Well, a CSV is a row-based text format. If you want to find the average temperature in a massive data set of weather logs, the query engine has to read every single line of text, parse out the temperature column, hold it in memory, and calculate it. It's incredibly slow. Apache Iceberg uses columnar file formats, specifically Apache Parquet. In a Parquet file, all the temperature data is stored together in one continuous physical block. The query engine just grabs that one block and ignores the rest of the file. Furthermore, Iceberg sits on top of S3 and provides database-like features. ACID transactions to prevent corrupt reads during writes, schema evolution so you can add new columns without breaking old data, and time travel so you can query what the data looked like yesterday.
Okay, so Iceberg on S3 is powerful. But the documentation highlights that managing this manually inevitably leads to a massive architectural headache known as the small files problem. What physically causes the small files problem?
Think about a high-frequency streaming architecture. You have thousands of IoT sensors on a factory floor sending temperature readings every single second. If your streaming engine writes those readings directly into the S3 data lake as they arrive, you end up creating thousands or millions of tiny little 5 kilobyte Parquet files. When your analytics engine goes to execute a query across that data, it has to consult the Iceberg metadata catalog to find the files, and then it has to open, read, and close millions of individual file headers on S3. The list requests overwhelm the system. The network overhead of opening and closing files eclipses the actual data processing time. The query engine literally chokes on the metadata.
So a query that should take 10 seconds takes 3 hours and costs a fortune in S3 API GET requests.
Exactly. The industry standard solution to the small files problem is a maintenance task called compaction. You have to run a background compute job that sweeps up thousands of these tiny files, decompresses them, merges them together, and writes them back out as a few large, highly optimized 512 megabyte Parquet files.
But historically, doing that required a team of dedicated data engineers. They had to write Apache Spark jobs, schedule them on EMR clusters, monitor them for failures, and pay the EC2 compute costs just to keep the storage tidy.
And that is exactly what AWS looked at and said, let us handle the heavy lifting. S3 Tables is a brand new type of table bucket, built explicitly and exclusively for tabular data using the Apache Iceberg format. You do not dump random images or raw text files in here. You create structured namespaces and tables.
And crucially, S3 Tables runs continuous automatic background maintenance for you. It solves the small files problem natively.
It does. It automatically compacts your files using advanced strategies without you provisioning a single server. It can use bin pack compaction, which simply groups small files together until they reach a target megabyte size. It can use sort compaction, physically reorganizing the data rows by specific columns to make downstream filtering faster. It can even use Z-order compaction, which interleaves values from multiple columns into a multidimensional curve if your data scientists frequently query across several different dimensions simultaneously.
It's zero ops maintenance. It manages the snapshots, it expires old data, it cleans up unreferenced orphan files, and the benchmark results in the sources are stark. By letting S3 natively manage the Apache Iceberg structure, it delivers up to 3 times faster query throughput and 10 times higher transactions per second compared to a self-managed Iceberg setup on a general-purpose bucket. You trade away a bit of direct manual control over the underlying files, and in return, you get massive operational efficiency. But S3 Tables solves the structured analytics problem, rows and columns. What about the unstructured problem? How does S3 fit into the massive generative AI boom? Because AI models don't just read tables. They read PDFs, documentation, and raw text.
To understand the S3 AI integration, we have to look at how foundation models, the large language models powering AI today, actually interact with external knowledge. An AI model might know the general universal recipe for scrambled eggs because it ingested Wikipedia and the open internet during its initial training phase, but it does not know your company's proprietary secret recipe stored in a confidential PDF.
Right. If a customer is interacting with an AI chatbot on my enterprise platform, and they ask a specific question about our internal operating procedures, I don't want the AI hallucinating a generic answer based on Reddit threads. I want the AI's response strictly grounded in my actual secure data.
That process of grounding an AI is an architectural pattern called RA, Retrieval Augmented Generation. When the user asks a question, the system pauses. It searches your massive internal document repository, retrieves the 3 or 4 relevant paragraphs, and sends those specific paragraphs to the AI alongside the user's prompt. The system essentially says, answer the user's question, but use only this provided context.
But here is the mechanical problem with egg. How does a computer system search a massive repository of PDFs for meaning? If the user asks about scrambled eggs, and the system does a basic keyword search for the exact word egg, it might completely miss a critical document that only uses the word yolk or omelet. Keyword searches don't understand context.
And this brings us to the breakthrough of S3 vectors. S3 introduces another specialized bucket type, the vector bucket. Instead of just storing the raw PDF file or the JPEG, it stores the mathematical embeddings of that file.
Okay, we need to pause and explain embeddings, because this is the core of modern AI. What physically is an embedding?
An embedding is an array of floating point numbers that represents the semantic meaning of a piece of unstructured data. You take a paragraph of text, you run it through an embedding model, and it outputs a vector, a long string of maybe 1,000 numbers. Those numbers are coordinates. They position that specific concept in a multidimensional mathematical space.
So it maps human language to a graph.
Exactly. And the magic of this multidimensional space is that concepts that mean similar things end up physically closer together on that graph. The mathematical vector coordinates for egg will sit extremely close to the coordinates for yolk, breakfast, and omelet, even though those words share 0 common letters.
So it's mapping relationships.
Yes. This enables what we call similarity search. When the user asks the chatbot, "What's in the scrambled eggs?" the system takes that question and converts it into its own vector coordinate. The S3 vector bucket then performs a mathematical calculation, usually measuring the cosine distance between coordinates, to find the stored document vectors that are physically closest to the question's vector.
It's not looking for the word egg, it's looking for the concept of eggs.
Precisely. It retrieves those exact conceptually relevant chunks of your proprietary recipe and feeds them into the large language model.
That is just incredible. We were watching S3 transform from a dumb filing cabinet into an active semantic memory bank for artificial intelligence. And because it integrates natively with AWS services like Bedrock Knowledge Bases, enterprise teams don't even have to stand up, secure, and manage a separate, complex vector database infrastructure. S3 just natively handles the mathematical similarity search, which naturally brings us to our final frontier. Because if S3 is now acting as the semantic brain for corporate AI, a high-speed Apache Iceberg Analytics lake for financial data, and a globally distributed file system, securing and governing this data is no longer just a compliance checklist item. It is a matter of corporate survival. How do massive enterprises ensure that this critical data isn't altered, accidentally exposed to the internet, or corrupted by a ransomware attack?
The cornerstone of enterprise data security is immutability, and S3 achieves absolute immutability through a mechanism called S3 Object Lock, which was built to replace older, clunkier legacy compliance features. S3 Object Lock provides rigorous worm protection.
Right, once read many.
Exactly. You write the object into the bucket, and then it is cryptographically locked at the infrastructure level. It cannot be deleted, modified, or overwritten for a strictly defined retention period, even by the person who uploaded it. And S3 Object Lock offers 2 distinct operational modes: governance mode and compliance mode.
Let's distinguish between the two. What is governance mode?
Governance mode is a strong internal safeguard. The lock protects the object against accidental deletion or modification by normal users, automated scripts, or rogue applications. However, select highly trusted administrators with specific elevated IAM permissions possess a mathematical key to bypass the lock if they have a legitimate business emergency and need to alter the file. It's a robust lock, but it has an audited backdoor.
And compliance mode?
Compliance mode has no backdoor, none. Once you lock an object in compliance mode, nobody can delete or overwrite it until the retention period naturally expires. The system administrator cannot delete it. The root user of the entire AWS account cannot delete it. Even if you call AWS support and beg them to delete it, they mathematically cannot. The protection is absolute. It is designed explicitly to meet the most draconian regulatory requirements on Earth, like SEC Rule 17A4 for financial records.
You literally lock the vault and throw away the key.
Yeah.
And the sources also mention a parallel feature called legal holds. How does that fit in?
A legal hold is a separate, indefinite lock that operates independently of the retention periods. You apply it to an object, usually during a legal audit, an e-discovery process, or active litigation. It completely prevents deletion of the file until an administrator explicitly removes the legal hold, regardless of whether a standard retention period has expired or not. It freezes the data for the lawyers.
Okay, so Object Lock absolutely guarantees the data isn't deleted or encrypted by ransomware. But what about making sure the data isn't corrupted across regions during a massive disaster? I want to dive deep into the Bridgewater case study mentioned in the sources because it perfectly illustrates the friction between massive scale and data integrity. Bridgewater is one of the world's largest and most sophisticated hedge funds. They manage a 10-petabyte data lake on S3, comprising over 100 billion individual objects. How do you handle disaster recovery at that scale?
At 10 petabytes, you can't just run a nightly backup script. Bridgewater relies heavily on S3 cross-region replication, or CRR, to continuously copy their entire data lake from their primary AWS region to a secondary, geographically isolated backup region. But in doing so, they encountered a fundamental challenge of distributed systems. S3 replication is highly durable, but it is asynchronous.
Let's explain the physical reality of asynchronous replication. It means it happens in the background eventually. It's not instantaneous.
Correct. AWS guarantees it will get there, but it doesn't guarantee when, and more importantly, it doesn't guarantee the order of arrival. Let's simulate a scenario. An application writes an Apache Iceberg table update to the primary region. That update consists of 3 files: File A, File B, and then a metadata manifest, File C, that points to the new data. The primary region receives them securely. The S3 replication engine picks them up and starts copying them to the backup region over the global network. Because it's asynchronous and running in parallel, the files might arrive out of order. The backup region might receive the metadata manifest, file C, first. Then it receives file A. But file B is delayed due to a micro-congestion event on the network.
Okay, so let's pause the sending action right there. It's 2:00 p.m. on a Tuesday. The primary region suddenly suffers a catastrophic power failure and goes completely offline. The replication is halted. The backup region is now the sole source of truth, but it's in a corrupted intermediate state. It has the manifest saying, read file A and file B, but file B hasn't arrived. If Bridgewater's financial analytics engine boots up in the backup region and tries to run a trading algorithm on that iceberg table, it's going to hit a missing file error, or worse, generate wildly incorrect financial models based on partial data.
Exactly. Eventual consistency is unacceptable for real-time financial modeling. So Bridgewater's engineers designed a brilliant state reconciliation architecture to guarantee absolute consistency. They realized they couldn't just trust the raw presence of files in the S3 backup bucket. They needed a source of truth. So they built an immutable commit table stored in a completely different database, Amazon DynamoDB.
Like a Git commit history, but for a petabyte-scale data lake.
Precisely. The DynamoDB commit table acts as an authoritative pointer to the fully verified holistic state of the S3 tables. As S3 objects replicate across the country, Bridgewater runs parallel, serverless compute processes that crack the replication status of every single individual file. The DynamoDB commit table in the backup region is only updated to point to a new table state when 100% of the data files and the metadata files associated with that specific transaction have been cryptographically confirmed as fully replicated and resting safely in the backup bucket.
So the downstream analytics tools, the trading algorithms, are completely blind to the raw S3 bucket. They only ever read from the verified commits listed in DynamoDB. Even if files are actively replicating out of order and sitting in the backup bucket, the analytics engine ignores them until the commit is officially published in DynamoDB saying this entire state is verified.
It's beautiful engineering. They have successfully built strong consistency on top of an inherently, eventually consistent replication engine. It mathematically ensures their financial models never read partially replicated, corrupted data during a chaotic disaster recovery scenario.
We also need to touch on active governance, protecting data from external threats and human error. The sources highlight two critical mechanisms here: block public access and Amazon Macy.
Block public access is, without hyperbole, arguably the most important security button in the entire AWS console. Historically, complex IAM policies or accidental bucket ACL changes have led to massive, headline-making data leaks where an engineer accidentally exposed a bucket of sensitive customer data to the open internet. When you turn on block public access at the account level, it acts as an absolute overriding veto. It mathematically overrides any individual bucket policy, any access control list, or any user command that attempts to make an object public. It ensures the data remains private regardless of what misconfigurations occur lower down in the stack.
It is a literal lifesaver for a CTO's career. And Amazon Macy.
Macy is an automated, machine learning-driven security service. When enabled, it continuously and transparently scans the contents of your S3 buckets looking for personally identifiable information PII. It knows how to identify credit card numbers, social security numbers, API keys, and passport formats. It actively audits your massive data lake and generates high-priority alerts if it discovers sensitive data sitting in buckets where it fundamentally shouldn't be. It gives security teams visibility into petabytes of data they couldn't possibly audit manually.
Okay, so we've locked the data with worm compliance, we've replicated the data with DynamoDB state tracking, we've blocked the public internet, and we've scanned the data with ML. But what if we want to fundamentally change the data in the exact moment it is being requested? This brings us to the final and arguably most futuristic feature we need to discuss: S3 Object Lambda.
S3 Object Lambda represents a blurring of the lines between storage and compute. Traditionally, if you stored a document in S3 that contained sensitive PII and you needed to display that document to a lower privileged user, say a customer service rep who shouldn't see the full social security number, you had a clunky workflow. You either had to run a batch job to create a second, permanently redacted copy of the file in S3, doubling your storage costs, or you had to download the full file to an intermediate EC2 server, run a redaction script, and then serve it to the user, adding latency and infrastructure overhead.
Both of those options are expensive and fragile. How does Object Lambda change the physics of that request?
Object Lambda allows you to attach an AWS Lambda function, a serverless snippet of your own custom code directly into the path of an S3 GET request. When the customer service application requests the file, S3 intercepts that YT request mid-flight. It racks the raw file to your custom Lambda code. The code processes, modifies, or redacts the data in memory, and then S3 returns only the dynamically modified data to the requesting application.
So the raw, unredacted file sits perfectly safe and untouched in the S3 bucket, but the application receives a completely customized redacted version on the fly.
Exactly. You are injecting active compute directly into the storage retrieval path. Redacting PII is just one use case. You can use Object Lambda to dynamically resize high-resolution images to thumbnails based on the device requesting them. You can use it to translate text files into different languages on the fly. You can use it to filter out specific rows of a massive CSV file before it hits a data scientist's laptop. It treats storage not as static files, but as dynamic, programmable endpoints.
Which brings us to the ultimate synthesis of this entire journey. What does this massive architectural deep dive mean for the engineers and the technologists listening? We have covered an immense amount of ground. We've seen how S3 evolved from a simple malloc for the internet, a basic key value abstraction, into an auto-scaling, geographically dispersed data engine. We've explored how it functions as an Apache Iceberg lakehouse, completely managing tabular data compaction natively. We've seen how it operates as a semantic memory bank for generative AI, performing complex multidimensional similarity searches on vector embeddings.
We've dissected the physics of maximizing global throughput using transfer acceleration and TCP saturation, and we've navigated the intricate multidimensional economics of balancing 11 nines of durability across 8 radically different storage classes, from the blistering single AZ speed of Express 1 zone to the deep freeze of Glacier archive.
And the fundamental takeaway here is that understanding these underlying mechanics, knowing how a distributed hash table handles prefixes, knowing why a 40 kilobyte metadata charge can bankrupt an archive project, knowing when to physically co-locate compute and storage to shave off milliseconds. This knowledge is the absolute difference between building an application that is sluggish, fragile, and wildly expensive, and building one that is lightning fast, highly resilient, and aggressively cost-optimized.
It is the stark difference between simply using a tool blindly and truly mastering the physics of cloud infrastructure.
Which leaves us with a final provocative concept to mull over. If S3 is now actively compacting Apache Iceberg data tables with serverless background jobs, if it is natively performing complex mathematical vector similarity searches for large language models, and if it is intercepting network requests to run Python code and dynamically mutate data on the fly,
it forces us to ask, is it even mathematically accurate to call S3 storage anymore? Or has the rigid historical line between the database, the compute engine, and the hard drive completely and permanently dissolved?
a fascinating structural shift to end on. Thank you so much for joining us on this incredibly deep dive. We encourage you to look at the buckets in your own architecture tomorrow morning and think differently about the invisible, highly evolved infrastructure powering your daily digital life. See you next time.